Let's talk about functions and surfaces. In this section, we're going to start with the idea of two variable functions. Functions of two variables, of course, we're going to be looking at functions of two or more variables a lot in this course in later sections. That's why your book is a multivariable book. It's multivariable calculus, more than one variable in our function. So here's a general idea for a two variable function. We're going to let f, very clever name for a function, isn't it, be a function. And it's going to go from the set of R cross R. In other words, that's a set of all ordered pairs. So that's the set of ordered pairs into just R. So in other words, F is going to take an ordered pair and send it to a number. All right, so let's just ordered pair gets sent to just a single real number. And that's just the basic idea of what we mean by a two variable function. Okay, and of course, looking ahead a little bit, a multivariable function, a three variable or four variable, we take an ordered triple or an ordered quadruple and send that to a real number with some formula. And so if you think about some of the issues that are going to arise when we have multivariable functions, one of those is domain. And if we talk about the domain of a two variable function, we can no longer talk about just simply a subset of the real numbers. We have to talk about a subset of where our ordered pairs live, which is in R2 on our xy plane. So the domain of a two variable function is a subset of R2, which again we represent graphically with the xy plane. And quick note about notation here as well. A lot of times we call the output of our two variable function z. Z being equal to f of x comma y. And so that's the output. That would be a function of two variables, just like we call the output of a single variable function y a lot of times, the output of a two variable function. We usually call z. Here x and y are our independent variables, and z then is the dependent variable because it depends on what we choose for our ordered pair x comma y. So the main thing I want to focus on right now, however, is this domain issue, and I want to look at a couple of examples of how we represent our domain for two variable functions. So we're going to play a little game called Find the Domain. And let's start with our first example. I'll call it example A because it's our first example, and A is the first letter in the alphabet. If you don't believe me, ask my daughter. F of xy is equal to the natural log of y minus x squared. Now, what has to be true about the natural log? Well, remember your natural log function. Just a quick review of natural log. Y equals the natural log of x looks like this. Remember, it's the inverse of the e to the x function. What's the domain of the natural log function in general? If you just take your natural log function, what can you put into that? Well, only positive numbers, right? You can't take the natural log of a negative number or 0. So whatever I put into my natural log function has to be positive. So returning to our problem here, that means the argument of our natural log function, y minus x squared, also has to be positive, strictly greater than 0. You can't take the log of 0 either. The reason for that, of course, is that you can't find a power on e that'll give you 0. So that's why you can't take the natural log of 0. So that means we need y to be greater than x squared. We can represent this with set notation. It's all ordered pairs x, y as long as the second coordinate is bigger than the first coordinate squared. Any ordered pair of that form will work in our two variable function. But a lot of times we're going to represent these graphically as well. So here is our xy plane. We said the domain of a two variable function is a subset of R2, which we represent with the xy plane. I'm going to draw in y equals x squared with a dotted or dashed line because it's not included in my domain. We want everything above that, don't we? So I would then shade in everything above that because we want the y values that are greater than x squared. We want the y coordinate to be bigger than x squared, so we want all the ordered pairs that lie above this parabola y equals x squared. That's our domain for that two-variable function. Okay? Hopefully you're getting the idea. Let's look at a couple more examples. Let's see, what should I call this example? How about, how about example B? Here f of xy, two-variable function, is equal to the square root of y plus 2x minus 3, all divided by y minus 2. Couple of domain issues here. As you know, you cannot divide by 0, so we need to make sure that y minus 2, that denominator of our function, is never 0. That means y can't be equal to 2. So any of our ordered pairs we put in here, we have to make sure that the y coordinate is never 2. We have another issue here with what's underneath the radical dude. We need to make sure we never take the square root of a negative number. So I need this to be greater than or equal to 0. Solving this for y means I need y to be greater than or equal to negative 2x plus 3. So again, one way we can represent this is with our set notation. The set of all ordered pairs, this is our domain. D, it's equal to the set of all ordered pairs x, y such that the y coordinate is greater than or equal to negative 2x plus 3 and y is not 2. So any ordered pair of that form will do the trick, but it may mean more to us if we can represent this graphically. So let's go ahead and try and do that. Here is our x, y plane. Domain is a subset of that. We have y equals 2. I'm going to go ahead and draw a dashed line here. So we can't be on that line, and we represent that usually, as I mentioned earlier, with a dotted or dashed line. So we can't have any ordered pairs that are on that line. That's where y is equal to 2. And we also have to make sure that we are on or above the line negative 2x plus 3. Now, y equals negative 2x plus 3 is a line with a slope of negative 2, a y-intercept of 0, 3. So down 2 to the right 1. Let me get a couple marks here for x. Down 2 to the right 1, down 2 to the right 1, and so on. So I'm going to do a solid line here. Whoops, see if I can make it a line. A solid line, because we can be on this line. Y can be equal to negative 2x minus 3. That means we just be taking the square root of 0 up here, and the square root of 0 is 0. But I want the y's that are greater than or equal to that, so on or above that. So anything of this form, we shade in everything on or above this purple line, but again that what am I saying? That blue line indicates we can't be on that horizontal line. We can't be on that line where y is equal to 2. So any ordered pair from the shaded in region, on or above this purple line, as long as it doesn't fall on that dotted line, is good to go for our domain of this function. We'll get a real number out if we put an ordered pair in from that region. All right, let's try maybe one more example here. I think we got time for one more, don't you? Let's see if I can figure out how to write on this thing. There we go. This one is called, as you may have guessed, example C. Here's my two-variable function, f of x, y. It's going to be equal to, in this case, another rational function, a fraction, if you will, x squared plus y over x squared plus y squared minus 4. Again, the only thing we have to worry about here is the denominator equaling 0. So I have to make sure that x squared plus y squared minus 4 is never 0, which means I need x squared plus y squared to not be equal to 4. Now, if you think about what that is, here's our domain in set notation form. Well, x squared plus y squared equals 4, as you know, is a circle of radius 2. Circle, radius is 2, center is the origin 0, 0. So I'm going to indicate basically that I can use any ordered pair in R2 except for ordered pairs that fall on that circle of radius 2. So again, a dotted or dashed line, or dashed circle in this case, would indicate that. And this is how I would represent graphically my domain of this function. Take any ordered pair you want, as long as you don't pick it to be an ordered pair on that circle. All right, next thing we want to look at then are the graphs of two variable functions. So let's turn our attention to that. We know how to graph single variable functions. When we take a single variable function and draw the graph, we usually get a curve or something in 2 dimensions. So the graph of a two variable function is going to be something in 3 dimensions. So let's take a look here. The graph of a function f of x, y is all points x, y, z in R3, that 3-dimensional space, so ordered triples there, such that that z coordinate is the output of the function when I put x and y into that 2-variable function. And again, some examples are going to be the most instructive here to see what's going on. We'll start with a very simple one. How about the function f of x, y equals 2, or if you like, we can call the output z, so we just have z equals 2. It's a constant function. The z value is always going to be 2, so let's think about what that looks like. We can put anything we want in for x and y. Here's z, x, y. As long as, it doesn't matter what we put in, the output's always going to be 2, so the height of this function, the height of the surface is always going to be 2, so it's going to be basically a plane that crosses the z-axis at 2. So we have a plane parallel to the xy plane through z equals 2. Okay, so again, the domain here, by the way, is all real numbers cross all real numbers, or R2. We can pick any ordered pair we want and put it in here. We're always going to get 2 out. Let's try another example. Suppose I have the 2-variable function f of x, y, and it's equal to negative 2x minus 4y plus 8. So this one's a little bit more difficult to draw unless we think about it a certain way. Again, you can call the output of your 2-variable function z, especially if we're going to be graphing it on the x, y, z coordinate axes. Now, does this look anything familiar to you, like anything that's familiar to you, like anything we've seen already in this course? You have all 3 variables. They're all to the first power. The linear type of function, linear type functions in R3 are planes. Maybe it's plain to see now, pun intended, if I put the x and the y term on the left side. Yeah, this is just the standard equation of a plane with a normal vector. Remember how we find the normal vector to a plane off of the standard equation. It's the coefficients of x, y, and z in that standard form. A normal vector n of 2, 4, 1. Now, how can we represent this graphically? Well, we can find the intercept is a good way to draw the plane. Notice that if we're, say, on the x-axis, so let's suppose I want to find where I cross the x-axis. Well, if I'm on the x-axis, then both y and z are 0. If I put 0 in for y and 0 in for z in my equation, I'm left with 2x equals 8, or x equals 4. So I'm going to intercept the x-axis at 4. Where would I intercept the y-axis? Well, let's think about it. If you put 0 in for x and 0 in for z, you'd have 4y equals 8. So y would be equal to 2. And where would I intercept the z-axis? I'll put 0 in for x and 0 in for y. That means I'd be on the z-axis. Z equals 8. So I have that point right there. Connecting these 3 points with straight lines is going to give us basically a picture of what this plane looks like in the first octave, where x, y, and z are all positive. Of course, you could shade that in. It'll extend infinitely far in all directions, but it's a nice visual representation of what that plane looks like. All right. Maybe 1 or 2 more here. Let's go with example C. Let's suppose I want to sketch the graph of f of x, y equals y squared. That is to say, I want z is equal to y squared. Well, here we have no stipulations on x, you'll notice. X can be anything we want it to be. Our domain is going to be all real numbers cross all real numbers. I can put any ordered pair I want in there. It's just that the output only depends on what I put in for y. I'm just going to square the y value, and that'll be my z. So z equals y squared, you say, well, that reminds me of the equation of a parabola, and that's exactly what it is. On the yz plane, I would have this parabola z equals y squared that would look something like this. But remember, x can be whatever we want it to be, so we're going to actually have this thing is going to look the same no matter where I'm at on the x-axis. I can extend it infinitely far in the positive and negative x direction. Back that up there. And I hope you get the idea. I don't want to screw this up too bad. But I have this parabolic cylinder, was what this is called. A parabolic cylinder. Some of your friends who drink a lot of Mountain Dew may refer to this as a half pipe. They may actually say it as like this. That's a half pipe, dude. So it's a parabolic cylinder again on the YZ plane. It's just that parabola. No stipulations on x, so we can extend that out as far as we want in the positive and negative x direction. Oh man, we're on a roll. Let's just keep going, huh? Here's another example. I want f of xy to equal x squared plus y squared. That is, I want z to be x squared plus y squared. No stipulations on our domain here. Any number you put in for x and y, you can square them and add them together, so no problems there. But here we're going to look at level curves. All right, so let me start this way. Let's suppose I have z being equal to 0 in this equation here. 0 being equal to x squared plus y squared. Well, this has only one solution, and that is 0, 0, right? I have to put in 0 for x and 0 for y. So I'm going to start by saying, okay, when z is 0, the only point that makes that true is going to be the origin. So I have this point 0, 0, 0 here. All right, now let's say we want z to be equal to 1. Well, then I have 1 equals x squared plus y squared. Now on the xy plane, maybe I can get a picture of the xy plane here someplace. Let me just squeeze it in right here. So just looking at the xy plane, we said when we have the point 0, 0, when z was equal to 0. On the xy plane, when z is equal to 1, I have x squared plus y squared equals 1. That's just a circle of radius 1. I'm going to draw that circle at a height of z equals 1. So here's that circle, but it's raised up to that plane where z is equal to 1. Let's do another one here, and I think we'll get the idea. How about if I let z be equal to 4? I want the output to be 4. I have 4 equals x squared plus y squared. We recognize that on the xy plane as a circle of radius 2. I'm going to put that circle of radius 2 at a height of z equals 4. And there you have it. Okay. And so, kind of connecting these points, of course, we could let z be anything in between. And here's what we get. This solid right here. This is what's called a paraboloid. More on these in a little bit.